pleasure to be here today and see so many of you here that you can make it. It's a big day for me. The title of my PhD work is Biobased Carbon Fibers from Solution Spun Lignocellulosic Precursors. My plan is to give a brief introduction to put my work into context, and then I will go on with my key findings and then conclude my work. But first, I just want to show the errata, 2 major erratas I found, and I've also printed erratas, so you can have a look at that if you want to. However, just as Professor Ganser pointed out, carbon fibers are used in application where lightweight is desired, and I would say also where performance is very important. Carbon fibers are, the demand for carbon fibers is growing because we need more lightweight materials, and it would be, for example, beneficial if we could use it in the mainstream automotive. But what is carbon fiber? Well, it's actually what it sounds like. It's very thin fibers, and they are comprised of more or less only carbon atoms. The structure is, I would say, graphite-like. One very good thing with carbon fibers is that you can tailor the mechanical properties. And it's also having a very low density. And the combination of having high mechanical properties and a low density is what makes it a lightweight material. And today it's more or less only manufactured from a fossil-based precursor, polyacrylonitrile or PAN. Minor shares are made from pitch, coal tar pitch, and cellulose. This is the problem. Carbon fibers are expensive, and they are made from non-renewable sources. And I think the opportunity may be found here in the forest. And more specifically, if we could use lignin and cellulose, 2 major wood components. Both polymers are highly available from, for example, the Kraft process. Lignin has a high carbon content, which is good if you want to make a carbon fiber. Cellulose, on the other hand, it has a lower carbon content, but it is a strong and linear polymer, and you can orient it, which is very important. So, if we now want to make a carbon fiber from lignin and cellulose, and we want to blend these 2 together, how would we do it? I think it's important to know a little bit about the manufacturing process to understand it. So you start with your precursor, and then you treat it in several consecutive thermal steps into a carbon fiber. And the purpose, basically what you do here, is that you remove all atoms except the carbon atoms. That's the goal. Usually you do a stabilization step before the carbonization, which is it's to make a fiber stable to undergo the carbonization. I will come back to that later. And then optionally you can do this ultra-high treatment, which is called graphitization. What I really would like to emphasize here is that it's an energy-intensive process, consumes a lot of electricity. It's a continuous process where this stabilization step is the bottleneck because it takes the longest time. And the optimal conditions that you should use, exactly what temperatures and residence time you should use, depends on the precursor and also the target properties of the final carbon fiber. And now you may wonder how you make this precursor. Well, do this by fiber spinning. And if you want to spin fibers from a polymer, you have 2 options. Either you do it from a melt. So then you need to be able to melt your polymer, and then it needs to be thermoplastic. And then you can do melt spinning. And lignin is, for example, thermoplastic, so you can melt spin it. Cellulose is not. So if you want to blend lignin and cellulose, we cannot use melt spinning, but we can do it from solution. So you dissolve your polymers, basically. In my work, I have made carbon fibers from precursors, which have been spun with air gap spinning, and wet spinning. And as you can see in this figure, the extrusion, where you extrude the filaments, is above the coagulation bath. That is called air gap spinning. If it's a spinneret or the extrusion is performed in the coagulation bath, it's called wet spinning. Okay, and that brings us into the objectives of my PhD thesis. And it has been to develop bio-based carbon fibers from precursors consisting of a blend of softwood kraft lignin and cellulose pulp. And an important focus has been to increase the knowledge on how the precursor characteristics, for example, the composition of the precursor, and also the conversion conditions influence the carbon fiber quality. And what I mean with quality, or that is basically the yield of the process, because it's very important for cost reasons, the tensile properties, so the mechanical properties, and also the structure. I have divided this into 3 parts, the results. Part number 1 is batchwise conversion of ionic liquid-based precursors. Part 2 is continuous conversion of ionic liquid-based precursors. So the part 1, batchwise, is more proof of concept, and part 2 is to make it more industrial, more similar to industrial conversion, although it's in very small scale. And then part 3, I've looked into an alternative solvent system to this ionic liquid acetate. If you could make carbon fibers from lignin-cellulose precursors, which have been spun with this system. And I would like to clarify that the ionic liquid-based precursors, they have been spun by my colleague, Andreas Bengtsson, and not me. So the credit should be on her for that work. So part 1, and here I've looked into fundamental studies using batchwise conversion, using lignin-cellulose precursors with 70% lignin and 30% cellulose. And this was the approach. So I converted these fibers by mounting them on a graphite frame to prevent them from shrinkage, and this is important to maintain the orientation in the fibers. And sometimes also used just to put them in a ceramic crucible, and then I put them in the stabilization furnace, took that sample out, put it in the carbonization furnace. And then I take the sample out from that. And what I really would like to emphasize here is that you typically use very low heating rates and also cooling rates, actually, in the setup. And also the vast majority of the research, carbon fiber research you can find, is actually done with this kind of setup. It's convenient. You need small amounts of material. The first thing I looked into was the effect of lignin. And here I used the same stabilization and carbonization profile to just see the effect of the precursor composition. And here you can see the carbon fiber yield. It increases drastically if we make it from a lignin-cellulose precursor instead of only cellulose. And that is exactly what we wanted to see. This is the reason why we blend in lignin here. How about the mechanical properties then? Well, the mechanical properties, they decrease of the precursor if you blend in lignin. But after carbonization, conversion to carbon fiber, we see no significant difference. And this is, I would say, positive, because it means that we increase the yield, and I would say that the mechanical properties don't drop compared to pure cellulose. The next thing I studied was the stabilization step, because this is the most time-consuming step in conversion to carbon fiber, and it's the most expensive conversion step. And it's highly desirable to minimize the time here due to this. I would like to spend one slide on why do you want to stabilize cellulose and lignin specifically. When it comes to lignin, I said it's a thermoplastic, so if you heat it up too fast, it can melt together, and then you have a problem. So here you want to convert it to a thermoset. That is the purpose of the stabilization step. For cellulose, it is known that an oxidative pretreatment prior to the carbonization is beneficial for the yield. It promotes char formation. You have 2 competitive reaction pathways when you thermally degrade cellulose. So you push it towards shard formation. So what I've done is that I've used different stabilization profiles. A slow one, which I started to work with, which is, I would say, similar to what you typically use for melt-spun lignin fibers. Then I've increased the heating rate, basically. So the fast profile is 2 hours, and that is, I would say, similar or at least on par with pan stabilization, time-wise. And I've looked on the fibers before and after stabilization with differential scanning calorimetry, and you can see that the precursor has a TG, it's a glass transition temperature, so it softens upon heating. But after stabilization, it's gone. And this indicates that we have turned it into a thermoset, and that is exactly what I wanted to see. But how does the final carbon fibers look like? Well, I used scan electron microscopy on the carbon fibers, and I could see that the fibers have kept their fiber integrity. So no major fusion occurred, which is positive. This is exactly what we want to see. And even if we skip the oxidative treatment, the fibers have not melted together. And I would like to say that this is a very important result, because this has been one of the major problems with carbon fibers from only lignin. And we also studied what happens during the stabilization step with these fibers. And FTIR, Fourier transform infrared spectroscopy, is a good tool to monitor the stabilization reactions. And here you can see the fibers before and after stabilization. And my conclusion is that the fibers are oxidized, and you have a more dehydrated structure after the stabilization, because the hydroxyl band goes down, the carbonyl band goes up, and also in the fingerprint region, you can see that the carbon-oxygen bonds decrease. But how does the stabilization profile affect the final carbon fiber yield, the conversion yield? That's the next thing. And we can see that it is beneficial to use an oxidative pretreatment prior to carbonization. The yield goes down if you skip it. That is what I say my take-home message here. And to address this, to try to increase the yield further, because it's very important, I have also used a flame retardant. I have impregnated the fibers with an additive. And this little guy is well known to work well on cellulose. So it's not so novel, I would say. But if you use this flame retardant, the yield goes up significantly. And especially for the fibers that are instantly carbonized. And I think a very important, interesting result here is that the yield is more or less constant in spite of what profile you use. The next thing I looked into, what is the effect of this stabilization profile on the final carbon fiber tensile properties? And here you can see the strength on the y-axis and the modulus on the x-axis. And without this flame retardant, we have a modulus of about 65 GPa and a tensile strength of about 800 megapascals. But for the fibers that were impregnated with ADHP, this flame retardant, it dropped a little bit, and I think it's due to residual phosphorus in the carbon fibers. However, when it comes to carbon fibers, it's well known that it's beneficial to make thin fibers, because you decrease the risk for critical defects in the fibers. So we did thinner fibers, and then the mechanical properties go up. So there are two messages here in this slide. So the thinner the better, and residual phosphorus may be bad for the tensile properties. The next thing I've looked into is the effect of the carbonization conditions. When I started to work, we knew very little on what was, for example, the optimal temperature and so on. And I looked into the yield, how it's affected by the final carbonization temperature. So I kept the stabilization profile constant and I just looked at the carbonization conditions. And as you can see, the yield goes down, or the mass loss. It's the same thing. But at 800 degrees, it becomes more or less constant. And this is an indication that the initial pyrolysis is complete. And also, the carbon and oxygen content in the fibers, they do carbon increase up to 800,000 degrees, and the oxygen content goes down, whereafter very little happens. And it's often said that you should have around 90, there's no strict limit, but 90% carbon in your fiber. So if you take that as a truth, then we can say that we have a carbon fiber at about 800 degrees. So we need 800 to carbonize at least 800 degrees to make carbon fibers from lignin-cellulose precursors. And then, how about the mechanical properties? The modulus, or the stiffness of the fiber, goes up drastically, in particular between 600 and 800 degrees. And after, I would say, 1000 to 1200 degrees, it levels off. However, for the tensile strength, we have a maximum at 1000 degrees Celsius. So my conclusion from this is that there is no reason to carbonize above, say, 1000 degrees C, in this setup at least, I would say. To summarize part number 1, well, lignin-cellulose precursors can be converted to carbon fiber batchwise, and both lignin and this flame retardant increases the yield. And lignin is not detrimental for the carbon fiber tensile properties, and it seems possible to use a relatively short stabilization time. And a temperature of about 800 degrees is required to prepare carbon fibers from these precursors. And a different experimental setup is needed to take this to the next level, I would say, because we have limitations in this batchwise setup I used here in part 1 to use more relevant condition, industrial relevant conditions. And that brings us into part number 2, which is about continuous conversion of these fibers. And here I've used a very primitive setup, which consists of a winding unit and a tube furnace. And I've developed a 3-stage conversion protocol to make carbon fibers. And here I've used precursors with less lignin, actually, because the precursor becomes a bit stronger and more easy to handle if we decrease the lignin content. And what I really would like to say is that when I started work on this, it was a bit of a black box, and partly it is still today, actually. Very little information can be found in the scientific literature on continuous conversion trials. I mean, this is usually the secret from the manufacturers of carbon fiber. You can find a little bit in old patents and so on. Yes. So when I managed to make the first carbon fibers with this setup, I was very happy. Big step for me, but perhaps not a big step for mankind, or actually very, very small. But it took quite a few trials before I learned how to run this, and the startup phase seems to be very important to be successful here. And what I like to show here is that when you go to this conversion, continuous conversion, it's very, very important to see how the fibers behave in each step. And here you can see the stiffness of the Young's modulus and the tensile strength as a function of the stage here in this, when I use this setup. And what is very important here is that the strength goes down. So your fibers become weaker and then they become stronger at a certain point. And this is because you degrade the initial structure of lignin and cellulose, more specifically, or exactly cellulose, to be specific. And then you build up a new carbon structure suddenly. So then your mechanical properties drastically go up. And I've studied, for example, what happens during the stabilization. And this is 2D wide-angle X-ray scattering profiles. And as you can, what is important with these images is that in the precursor you can see that the red is high intensity and it's concentrated to one spot because you have a crystalline. It's come from the crystalline structure of cellulose and it's oriented. But after the stabilization, it gets smeared out, this red area, and that is because you start to make it amorphous. You break down the structure. Important to know. And this, because when you do continuous conversion and you want to stretch the fibers, and at a certain point, they are very weak, so you need to bear this in mind on exactly where you should have a high tension or low tension in your tow, for example. I also compared with Batchwise conversion, and as a comparison here, you can see the conversion time differs a lot. We have limitations here. The relative stretching, minus 10% means that you allow the fibers to shrink 10%. When you mount them on this graphite frame, it's constrained, so it's 0% there. However, the tensile strength of the carbon fibers, they were the same, but the modulus is not the same. And my conclusion here is that we need to work more, adjust the conversion profiles here. And I think the tension is the crucial part here. Work more on that. So to summarize part 2, well, we can continuously convert lignin-cellulose precursors to carbon fiber at industrially relevant processing times, and the conversion protocol needs to be adjusted. We need more research here. And this brings us into part 3. And here I've looked into an alternative way of making lignin-cellulose precursors. Ionic liquids, which are used to dissolve cellulose and lignin, they are very powerful, but they are relatively expensive and hard to recycle. So it would be beneficial if we could find an alternative solvent system when we make the precursor fibers. So here I've used cold alkali to co-dissolve cellulose and lignin to create a spin dope. And then I used classical wet spinning. And the fibers have been coagulated in 2 different coagulation bath compositions. System S, which is sulfuric acid and sodium sulfate, and system P, which is phosphoric acid and is flame retardant. And there are reasons for that. And then I spun precursors with 0 or 30% lignin, and then I've converted them both batchwise, and we had this continuous setup, or semi-continuous setup. And the first thing I looked into was the yield of the carbon fibers. And here you can see the yield for the carbon fibers made from the system S fibers, with and without lignin. And the lignin cellulose precursor increases the yield significantly, I would say, which is beneficial. This is the reason, again, why we want to incorporate lignin. However, if we use this system P fibers instead, the yield increases even more, in particular for the cellulose, the carbon fibers from the cellulose precursors. So it's, I mean, these trends are very similar to what I saw in part 1 on the ionic liquid-based precursors, basically. And then, how about the mechanical properties of these fibers? Well, this is batchwise derived carbon fibers. There is one sample that stands out. So you have the modulus, it's a black bar, and the red bar is the strength. And I would say they are slightly weaker than the carbon fibers from the ionic liquid-based precursors, but the difference is not extreme, I would say. And to understand a little bit more about, because there's one sample that stands out here, it's without lignin, actually. You can also see actually that this is the strongest precursor, and it's also the precursor that has the highest orientation. So that brings me to the conclusion that the precursor quality and the orientation is very important for the final carbon fiber properties. And my last slide, actually, before I start to summarize. And this is about the tension during continuous conversion. I've started to study this a little bit. And here you can see the modulus and the tensile strength. This is from pure cellulose precursor. I should clarify that, not with lignin. As a function of the fiber tension. So how much stress do you apply on your fibers during carbonization? And you can see the modulus goes up. However, I've not been able to obtain the same properties as I have obtained Batchwise yet, but working on it. And I've also studied the structures of the carbon fibers with wide-angle X-ray scattering, and one can see that the fibers with a higher modulus, they do have a more anisotropic structure. So the tension seems to be very important. So to summarize part number 3, lignin-cellulose precursors can be prepared. We have the cold alkali solvent system. Precursors, the precursors can be converted to carbon fiber. We have both batchwise and continuous conversion, and both lignin and the use of system P here when you spin the precursor increases the yield. And the carbon fiber tensile properties are affected by the precursor and the conversion conditions. And this is my general conclusion from my whole work. So we can make bio-based carbon fibers from solution spun lignin-cellulose precursor using softwood Kraft lignin and cellulose pulp. And the fibers can be processed to carbon fibers using both batchwise and continuous conversion. And the yield can be increased significantly by adding lignin and or a flame retardant. And the carbon fiber tensile properties are, I would say, general grade carbon fibers, comparable to, for example, isotropic pitch-based carbon fibers. And just very shortly about the future work, this list could be made very long, but I think in future we must work more on the continuous conversion. That will be the key to take this to the next level. Learn more exactly how we should process these fibers. And also stretch graphitization will probably be needed if you want to make carbon fibers that have significantly higher tensile properties, mechanical properties, so to speak. And I think alternative conversion techniques may be also an interesting topic for future work. For example, using more energy efficient conversion techniques, and also for example, pressure reduced stabilization has been shown recently to be able to increase the tensile properties of cellulose-based carbon fibers. And I also would like to highlight that the recovery of the solvent used in the precursor spinning will be very important, or it will be crucial in order to make this economically feasible in the future. And I would like to acknowledge some persons, agencies, and first and foremost my supervisors, Professor Monica Ek, Dr. Maria Sedin, Associate Professor Elisabeth Sjöholm, and Associate Professor Elisabeth Brännvall for the guidance and support throughout my work as a PhD student. And my collaborators at RISE in Mölndal, Jenny Bengtsson, Kerstin Gedvert, Tobias Könke, Doctor ×3, and also the lignin unit at RISE where I work, team there, and the funding agencies, Swedish Energy Agency, SCA, Valmet, Södra Forskningsstiftelse, and RISE. Thank you for your attention.
And now we will continue with